All right. So I just wanted to reiterate a couple things from last week, just because I know it was pretty quick, but this is a really important topic in general is time synchronization and something that does occur in every substation, whether it's conventional or digital. So I just want to make sure this is a concept that you understand, that we have always done time synchronization in substations. So the reason that we have to do this is because every device that exists in a substation does have capabilities of keeping its own time, or I guess I shouldn't say every device, but most of the devices that we use have capabilities of keeping their own time. So you might think, okay, we should just set them all to the same time, and then after we do that, everything's great, right? Why do we need to worry about continuous time synchronization? The reason is because clocks drift. And so you've probably seen this in your clock in your car, that if you just leave it as the same thing without adjusting it ever, over time it'll move into the future or move into the past. And for normal use, you'll notice it only when it gets like a minute out. So like 1 minute in one direction or the other direction. But if you wanted to look closely, you could even see a difference on the seconds time frame. But when we're talking about substation uses and time synchronization, especially if we're comparing waveforms, we're talking about accuracy to like 1 microsecond. And so that amount of drift with a normal clock is actually can take place over a very short time frame. So in your car, it'll take like a year to get out of date by a minute, but in a substation, an IED can drift a microsecond in even like 2 to 10 seconds of time. So that's why we need to do continuous time synchronization if we're dealing with things with digital substations, is because when we look at this, as if you don't have those IEDs being continuously time synchronized and they want to compare voltage waveforms that are sent on the network, over time they would get farther and farther apart and create more and more error. So what will happen is that they'll shift a little bit farther apart and then they'll synchronize and get closer again, and then they'll drift and do this over and over and over. So we just need to keep that maximum error under 1 microsecond for a digital substation. In a conventional substation, we're not comparing analog signals to that degree of specificity. So with a conventional substation, only need time accuracy to like 1 millisecond. So 1,000 times less accurate. So then that's why we can do it with older technology like iRig, which is the coax cable that goes to each IED. Um, so conventional, we're still using that, but even that is still synchronized using a GPS satellite. It's just instead of using our Ethernet network for our time signal synchronization, where we bring everything back together, every device needs its own coax cable going to it. So time synchronization is something it's important for conventional substations, but it's like incredibly important and much more complex for a digital substation. So along with that, I kind of we ended quickly talking about this stuff, but the network in a substation has always been important. But in a conventional substation, if the network goes down for a few seconds, a few minutes, it's not good, but it's not the end of your world. Of the world, your protection is still functioning. In a digital substation, as soon as the network goes down, even for 1 frame of Ethernet, then you don't have protection during that time. And so that's why we care so much more about the network when we're talking about a digital substation. So we have things that can handle that. So PRP and HSR, which I briefly mentioned last class, basically utilizing these two technologies on an Ethernet network, you can make it so that even if you have a single point of failure in your network, you never lose even 1 frame. And so that's why we can utilize an Ethernet network for those protection signals in a digital substation. So the other aspect that goes along with that is now we have a lot more cybersecurity concerns. We've always had cybersecurity concerns with anything that's utility, and it's widely understood that the next terrorist attack on American soil is likely going to actually be a cyber attack on our utilities. So if at all possible, the hackers want to get into a substation, they want to get into a gas pipeline control system, something like that, and then make it malfunction in some way. And so the conventional substation, that's always been a problem, that if they can get in and cause like circuit breakers to open, or they can lie about the status of the grid, so certain things that aren't expected to happen do happen, then they want to do that to kind of bring down our grid. But then once we're talking about a digital substation, everything becomes even more concerning because now you have more digital data. It's hard to hack a hardwired connection, like without physically being there. But as soon as everything's digital, now you have more basically what we call attack vectors. So there's more places where they can attack. So that's what this slide is about, is that there, with a conventional substation, there are plenty of ways that people can attack a substation. So basically, if they can get on the network, they can cause bad things to happen. It's pretty much guaranteed. It's more a question of how long does it take them to cause those bad things, or how can you limit them to the smallest area of doing bad things. So that's always even been the case with a conventional substation. With a digital substation, there are now new attack vectors that we would have to worry about. And so this is, again, one of the reasons we've seen kind of a slower rollout with digital substations, is they really want to make sure they understand these things before they have it fully in service. So one of them is the GPS spoofing, which is, I just talked about why that's so important with a digital substation, right? That if you lose a GPS signal, then you're not going to have your accurate time anymore. And now your signals, you can't do a differential protection anymore, basically. So once you lose the ability to do differential protection, you need to block those protection functions. You can still theoretically do like a simple overcurrent, but we do a lot of differential protection in general, and that protects some very important assets for us. So differential protection would be protecting things like transformers, underground lines, and underwater lines, that if somebody could attack those, that would be very, very bad because they're very expensive and take a long time to replace. So we really care about a differential protection. So without time synchronization on a digital substation, we can't do differential protection at all. So that's a strong attack vector for them. Essentially, with GPS spoofing, they show up with a signal that looks like a GPS satellite, except it lies about what time it is. So it's a lot simpler than you would think. Alternatively, they can also just do something to jam the signal, which would just make it so that nothing can see the GPS signals anymore. And then with digital substations again, now we have binary signals and analog waveforms that exist in a purely digital form on the network. Now, if an attacker can get onto the network that contains those signals, that's another attack vector that wouldn't be available in a conventional substation. And so one important aspect to that is right now, with analog waveforms and binary signals in substations, if it's a digital substation, we don't really do any authentication. So if somebody can get a computer onto the network, they can lie about what the current or voltage looks like, and they can lie about the status of a breaker being open or closed, or sending out signals to say to open something. We're not authenticating, like, is this the right person telling us these things? In the future, that will be introduced. It's just right now we don't do that. And then in terms of how we do deal with those threats, these are things that we've done for a long time on even conventional substations. This is kind of high level stuff to talk about, so I don't really have time to talk about it all today. You have these slides. These are things you can go and look up what these actually mean. But like, for example, network segmentation, it basically means don't put all of your assets on one network where everything can be attacked from that same location. Make it so that even if one area gets compromised, then there's separate areas that are still not compromised. That's the idea of network segmentation. And you would use firewalls and access control lists to do that. So you basically limit the ability of traffic to get from one network segment to another using a firewall or an access control list. We're also now commonly using intrusion detection systems. It's again something I recommend you look up if you're going to be going into the power industry. It's somewhat new, but they're widely implemented. Basically, with those, we can monitor all of the traffic in a substation, and we create like this baseline of what that traffic is supposed to look like. If it ever changes from what your expectation is, then you'll get alarms. And we have a few different ways to do that. Like one of them is like artificial intelligence based. Another is like a blacklisting or whitelisting approach. So if you were curious about how this stuff is actually implemented, there are guidelines, government regulations on how we need to actually handle cybersecurity and everything in a substation. And so those are the SIP requirements. So if you literally just Google like NERC SIP, you'll get to this web page and you can go and look at those actual requirements. SIP 15 is one that's coming out soon, and that's going to require actually intrusion detection systems in every substation. So we have ways of dealing now with the cybersecurity threats that come along with having a digital substation. But again, it's something that's still kind of new, so people are still figuring some of these things out. All right, so that was the leftover from last week. So now I want to jump into the new stuff from this week. Are there any questions on anything that was covered or I guess not last week, on Tuesday. Everything pretty straightforward. All right. Then the last presentation we have today is I wanted to do one actually on SCADA testing and commissioning. So the reason I'm doing this one actually is because I think it's something people do not do well right now. So we generally, when we build a substation, we do testing and commissioning. And I think in general, people have a very good understanding in the industry of how to test and commission protection, but they don't necessarily do the testing and commissioning of a SCADA network very well. I don't have time to go into super amounts of detail here for how that's done and everything, but I kind of want to give you a high level idea of like what are things that we should be looking for when we're testing and commissioning a network, and why do we do these things? So in general, in the substation design life cycle, we have these different kind of stages. And so you're going to have your very initial like thought ideas like space for it where it's like, okay, we need to look at the system and we need a new substation in this location. And then people are going to go through the actual design phase of like looking at how the substation needs to be designed, like what types of power capabilities does it need to be able to handle, and then they start actually implementing some of the designs. And so it goes through like a civil engineering phase where they're building the physical equipment or the physical building, and then they implement the actual electrical equipment. But then one of the last stages is commissioning. And so commissioning is what we basically do to say, yes, this substation is ready to go online. It can handle the load we're going to be putting onto it, but then also in fault conditions, it's going to operate correctly. Some of this can be a little bit different depending on if it's a green field or a brown field. I recommend that you write those vocabulary words down and remember them because that's something that will absolutely come up on a job. Like somebody will say like, oh, this is a greenfield project or this is a brownfield project. It's actually a pretty simple definition that greenfield would be when you're building something entirely new, and brownfield is when you're kind of retrofitting something that's old or replacing something that's old there. Um, so generally people like to design greenfields because then you basically have all the autonomy in the world to design something that's new and it's the best it could possibly be. Where with brownfield, you have to kind of deal with sunken costs from what it already exists there. So if we have like an electromechanical relay that we or substation that we need to update, then we can't just necessarily throw it all in the trash and then put all digital substation stuff in there. Usually what actually happens is we replace some of the electromechanical equipment with microprocessor based relays while keeping like 50% of what's there still functioning. And a lot of that's for cost reasons, but a lot of it can also be for time reasons that we don't necessarily have time to completely tear everything down and build a new one before we need the usability of this substation. Um, so in terms of what commissioning actually is, when we're testing for protective relay functionality, we will actually usually isolate the relays. And so when I say isolate, I mean have it not connected onto the power grid at all. And then we'll inject signals into the relay and then make sure it operates correctly. So in this class, you're going to be learning things about overcurrent curves and time current curves and everything. And with those, you basically set points where it's like if the current is at this level for a certain amount of time, then we're going to trip. But if it's at a lower level for a longer amount of time, then we'd also trip. And you end up with this curve. So when we test these relays during the commissioning and testing phase, then we will actually inject a current curve and make sure it operates at the right times. So that's something that we generally do very well. We have good procedures for how to do protective testing. And until you get into these really complex, weird schemes, I think people do a very good job of this. On the other hand, for SCADA, I think a lot of people leave a lot of things open to interpretation about how much it's actually tested. And I think it's a lot of lack of knowledge about how the system actually operates and what they should be testing for. So things that we do generally test for is we verify our gateways. So that's something I talked about on the first day where basically you have a substation, it's working on DMP3, MMS, it has some protocol for passing around data inside. And then you have like a control center somewhere else. And you need to pass data from the substation to that control center. And they're usually in two different protocols. Sometimes it is the same. But we verify that when we modify something in the substation, the control center sees it properly. It's very common for people to mean to put like point A on the substation onto point A on the control center, and it ends up in point B. And basically, that would tell the control center like some circuit breaker is open when it's actually closed, or give the status of the wrong device or something like that. So we need to verify that gateway operation. We also want to verify our signal values. So if something should be a 1 when it's closed and a 0 when it's open, then we want to verify that that is actually the case. We want to verify everything in the HMI. So make sure that like if we set something to a certain set point and that should show an analog value on the HMI, then we actually see that properly. But then also your HMI should reflect what is the status of the breaker? Is it open or closed? Um, does it show proper line values? Things like that. And then this last one is the sequence of events reporting. This one is actually very, very important. That it basically, and that's one of the things we actually need time synchronization for, is basically we have this log of all the things that have happened in the substation, and we keep that log to like the millisecond accuracy. And that would be in the event of like some failure, we go and look at the sequence of events report and we find out what was the order of events that happened leading up to that fault, and we can figure out what actually went wrong. Like, was it human error that somebody went in and they pushed buttons in a way they shouldn't have? Or was there actually an overcurrent that happened and that caused a cascade of events that we weren't expecting, something like that. So we want to verify all of these things in our commissioning standpoint before it goes into operation. These are things that we want to do later. Is kind of like, oh, did it work? We'll find out. So why do we need to do this? Like, this seems like a lot of effort, right? Like you would think, okay, we did a lot of work designing this. Why don't we just build it correctly and just implement it, right? But the big thing is it always comes back to money. So if you think about what your power company is selling, in my opinion, power companies are really not selling power. Like their electrons are the same as anyone else's electrons. Like there's no value added thing that they can do to their electricity. Really, what they are selling is their reliability. So you don't even really have the option of choosing between company A and company B, right? Unfortunately, that's just how our system has to work out. But essentially, how the utilities operate in terms of their profit model is on keeping uptime at the lowest cost. And so those two things need to be balanced out. So they can't spend trillions of dollars to make their power system perfect, but they also can't spend too little money and have a lot of failures. And so the utilities will actually receive fines from regulatory bodies based on if they have too much downtime. And then also during their downtime, they're not making money, right? They're not selling any electricity during times that they're not operating. So we actually have these different metrics, KD, SAIDI, and SAIFI. I have a separate slide on those here in just a second. But basically that just says how well does the utility perform in terms of these things. So we commission basically because we want to keep our power system online as much as possible. Otherwise, we're losing money. So protective events are going to be really, really rare. So like if you have an overcurrent, that means something bad happened. So option one, it was an actual fault where like a tree fell on a line, or you had a windstorm or a ice storm that knocked over something. A squirrel got into the transformer and shorted some coils, things like that. Um, so those are things that should happen very, very rarely. On the other side, somebody might misdesign something or or data isn't correct, and essentially we use too much current on one circuit. So some factory draws way more current than they were expected, or we put too many homes on one. You may have heard of like rolling blackouts where people are using air conditioning too much, like a giant group of people, and we didn't account for that. Um, so these protective events should be really, really rare, but they need to operate correctly when they do happen the first time. So we can't like implement a substation and then the first windstorm is 2 years later, and then we find out, oh, it never even operated correctly in the first place. And then when it doesn't operate correctly, you blow up a transformer, and then that substation is going to be out of commission for a year and a half while you get a new transformer. Um, so those are like, we cannot just rely on like, oh, well, when the first fault happens, we'll see if it actually works. Like we need to test that stuff ahead of time. So when we have a protection scheme, like when we actually have a fault, then we look at the SCR, the sequence of events reporting, and make sure everything happened correctly. That sequence of events is also what can tell us, like, if a protective event happens and we didn't expect it to, that would tell us why it went wrong, and now we can fix it. So that's another reason we really, really need to commission our sequence of events reporting accurately, because if it's not commissioned properly and we don't actually store the data we think we are, then when this like some random fault happens, we don't have any ability to figure it out. Like, why did it happen? Now it's just going to happen again. And now, okay, we fixed SCR, but now we need to wait for the same thing to happen again before now we can figure out why it happened in the first place. So this stuff is very, very important. And you can have regulatory, but then also legal consequences. Like, literally, CEOs of utilities can go to jail for this stuff not being recorded properly, if it kills people. So these are not. It is money, but there are very large legal consequences to not following these commissioning steps properly. So in terms of these metrics, I mentioned before, there's these different words for them. Like, they end up being a little simpler than you would think. So, like, customer average interruption duration, and then frequency for system and system duration frequency. Basically, these are just metrics that are calculated for the utility that rate how well they did. So, like, for example, in Maine, we have two power utilities. We have CMP and we have Versant. So CMP, you can see this right from their website. They have these 2023 PUC, which is the Public Utility Commission. This is their mandated reliability metrics. So if we go to that, actually, you can see what they said about what they actually did this year in terms of reliability. And so you can see these different terms: SAFE, SAIDI, and CAIDI. And these numbers, as an average person, they don't necessarily mean too much. Basically, it's some statistical analysis of, they figure that these are good metrics where if the utility is aiming to get these as low as possible, then they've designed a good utility. And so basically their goal is to get these as low as possible while spending the absolute minimum amount of money on upgrading the grid. Because if you spend too much and you make these metrics as close to zero as possible, you're going to lose money just from how you're spending. So that's public information that you can go and look at. But again, this is really why we care so much about our commissioning. Let's see, where was that one? Okay. So something to keep in mind, though, is we're not going to be perfect. And again, it comes down to money, is that we can't test everything. We can't have field engineers in there for months at a time testing literally every possible failure scenario in every case. So we need to design around that to make it so that there's very few edge cases that we can't test for. But something that you'll run into is, it's easy to test for things to happen that you expect. It's hard to test for everything that you don't expect to not happen, kind of, right? So for example, with an overcurrent curve, right? If you're testing that with protection, you can test that it's going to operate correctly on all of the time points that you've set out, right? But it's hard to test that any other current could possibly trip it in any other way that's not expected. So there's infinite amount of other possibilities, right? And you can't test them all. So we do our best to test, like, create test scenarios that make sense for what we need to happen, but you're going to always eventually run into something that you couldn't have even thought to test. And that's okay. I'm not saying that you need to test every possible one of infinite scenarios. So you do have to realize that reality. So in terms of communications, we do these signal tests to make sure that the signals are received properly, but then also if you send like a certain one, it should go through the internal logic and cause something else to happen. We test for that. But we can't necessarily test every combination of every signal at the same time. Because if you have 10, or let's say you have two signals, right? Then you might have just four states that you have to test, right? If they're both zeros, if they're both ones, one is a one and the other is a zero, and then swap those, you have four cases. But then as you get more and more signals, right, you're ending up with millions and millions of cases. We can't test all of those. So we test the ones that are what we're expecting to operate properly. And then we have multiple people look at the internal logic to make sure that things are set up properly from our previously designed systems as well that are in operation. Um, but for an example, we very commonly will misconfigure networking equipment, and that might cause communications that should not be able to get to like one device to actually then get there. And then if that device is also misconfigured to allow for something, then it will actually trip in that scenario. And that's something I have actually seen. And so with this, it's basically a cascade of failures. So something that I found in substations in general is it's very rarely one mistake that causes an issue. It's usually two mistakes working together at a minimum. So that's why we put a lot of effort into the commissioning and everything, that it's like if we can find 99.9% of mistakes, then it's very likely that you have those two mistakes that line up that actually do cause something bad to happen. So we want to we want to at least catch all the as many individual mistakes as we can. And again, that's usually misconfigurations from people not taking their time or copying and pasting. So this is a large aspect of testing that I think is not done properly, is network switch testing and commissioning. And there are two reasons that generally it's not done properly. Number one is that people don't actually understand networking in general. Like most of the field engineers that are out there that are doing commissioning, they're very good with protection and they're very good with understanding power systems. They don't understand IT. And I don't even really blame them. It's like IT is a whole degree in and of itself, and why would they have all that knowledge? So basically, they can follow procedures for how to do these tests, but it doesn't mean that they'll see when something is wrong and then react to it properly. So what we should actually be testing, or actually, I said there's 2 points, and I only said one of them. The other point that makes it really hard to test like network switches properly is that there's just so many possible testing scenarios and so many points to test. So if you have a 48 port switch, then you have 48 individual ports that you could plug into, right? And all of those should have different MAC addresses and IP addresses of devices associated on them. And then after that point, they have different protocols theoretically, but then they might also be configured in different ways. It's really hard for you to plug a piece of testing equipment into each one of those ports and actually make sure all of the communications are showing up properly, especially when some of those communications are intermittent. They're not always happening. So you have to like cause them to happen so then you can test it. And that would be 48 ports on just one switch. What if you have 10 switches, right? We don't have infinite amounts of time to do this testing. So they can't possibly test everything at every single port. So in terms of switch testing, like what do we actually need to test for a SCADA network? Why, what could go wrong? One of them is definitely security. So with network switches in general, if we are in a point where we need to worry about security for network switches, we turn off all of the ports that are not being used. That's like step one. But then a lot of the times we'll add authentication onto ports on the switches. So basically, then if you plug in a device that's not expected into that port, it shouldn't allow it to communicate. We also limit people's ability to log into the switches and make configuration changes from a lot of the different ports. And then we also might set up different like VLAN filtering, which kind of goes along with security. But there is a lot more that also goes along with VLANs. So of all the things I've just mentioned, right, those are all things that could be on each one of these ports. And again, we don't really have the time to test those. So instead of actually testing physically on the switch, usually what we'll actually do is verify the files that go into the switch. So like we'll verify the actual configuration of the switch either in the web interface, or some switches have like configuration files that we can take a look at and compare against. So can anyone think of what would be the big issue with looking at the configuration files versus actually walking into the switches and plugging in to test?
You might think that a file is going to work a certain way, especially like if it's, I know I've done it before where I code something and I think it's going to work a certain way and it ends up producing a unexpected result.
Yep, that is absolutely one of them that you're what you face in reality from the switch is not what you thought you configured, right? But you basically you did your configuration, you loaded in the files, and now it doesn't operate in that way. That would definitely be one of the two big ones, but then there's one other one. And I run into this all the time, but not necessarily even just with switches. This is a really common problem in general at looking at offline files. So the other really big one is, how do you know those are the actual files that are loaded into that device? So that's something that I've run into very, very commonly is people will audit or quality control these files, and they'll take a look at them and be like, yep, the files are great. And so then they say, okay, everything's ready to go into operation. It goes into operation. Now it's not working properly. So then and so like I used to work in the car industry and the factory floor. I'd run into this all the time. So then I'd like go out onto the floor, plug into one of the robot cells to see what's going on. And so the first thing I would do is I would use those files to go online with the device and verify things are operating correctly. And I would get a message saying, oh, the files that you have in offline don't match what's loaded into the device. And so then we realized that what we were troubleshooting the entire time, like doing quality control, were files that don't even actually, they weren't the ones that are in the device. So there's usually a couple failures that happen there is either somebody forgot to load in the new files or they made changes to the files offline without then uploading them back to the device again, or somebody came in and made changes to the device without updating other files. So there's a bunch of different scenarios that can happen. So that's where, again, it's really hard to test network switches because you need to not only verify the configuration of them as like files, really you should be verifying live values of the switch and making sure it matches your files. But that's also where like version control is very, very important when you work in industry. So several of you, I think, even work at contractors right now. Your company probably has policies about like when you grab files from the server, about storing them on your own computer and operating on or making changes to them rather than like working from the server. So then if somebody else tries to work on that file, they get like, oh, it's locked by somebody and you can't make changes right now, that kind of version control stuff. That's very, very important for exactly the reasons I've been stating here. Is like you want to make sure the files that are in the device match what you're trying to troubleshoot. And that's true for relays, switches, whatever. But um, that's one of the reasons it's really hard to commission network switches. VLANs is something that we use to filter traffic for switches, and it's something that's very commonly misconfigured, where basically people will configure VLANs so that then the traffic doesn't come out on the port that it's expected, or it's allowing traffic with VLAN tags that should not be allowed there. And again, it's hard to troubleshoot or commission because you would have to go and plug into literally every port on the switch and make sure the traffic is correct. We don't have time for that. So generally what we actually do is we port mirror all the traffic from a switch. So all the traffic from all the ports, we mirror it to another port, and then we monitor it from just that one port, and we make sure all the traffic that should be there is there, and that's it. Like we're not actually testing 100%. We're testing the positive case in that scenario, but we're not testing the negative case of like, or things showing up that shouldn't be there. Another really big one is redundancy, and this one is the one I'm most passionate about, actually. So I mentioned just in like the last slideshow, right, that we have these now with our network being considered critical infrastructure, it can't ever go down, like ever, if it's in a digital substation. So we've developed these different methods of redundancy, PRP and HSR to handle that. And so this is something I've seen a bunch of times in different utilities is that they won't actually test their redundancy. And so by testing redundancy, I mean like set up your network and then cause a failure and make sure your traffic is still performing correctly. So with PRP, which is one of the redundancy technologies I was talking about with Ethernet, basically you just have two paths on the network that are completely independent of each other. And if one of them fails, the traffic is still being sent on the other path. So the identical traffic is being sent in two places on your network, and both of them will show up at the other device. Whichever, like if one of them fails, the other one is still arriving just fine. So what I've seen with the commissioning for that is people will set up the network, they'll plug in all the IEDs, and then for their testing, they just test if the device can see the signal. So what would be the problem with that? If they look at the IED, it can see whatever signal it's supposed to be seeing, and they say, okay, our network is working. What would be the issue there? It's okay if this question's a little hard for you.
Is it would it if you're not getting one of the signals, but one's going through?
Yes,
I mean,
exactly.
yeah.
Yeah. So that's exactly the problem that people will do all the time is they'll set up stuff, they see that the signal is there, like they operate a circuit breaker, either real or simulator or something, they see it show up on the device and they're like, okay, our network is working fine. The thing is, it might have only been on one of those redundant channels, and so then it would have still showed up. So they're not going to actually know they had a problem until one of their network sides fails, and then they'll lose basically all of their messages. And so the reason that this makes me so upset is because when you install additional redundancy like PRP and HSR, there's a significant cost that goes along with it. There's an engineering cost, but then in terms of PRP, you actually have to duplicate your network. So for every switch you were buying, which was like $2,000 to $5,000, with PRP you have to buy a complete duplicate of it so you can send the traffic in two directions. So you're basically spending twice as much money on your network, and you're spending a lot of engineering time. So then if you do all of that and then you don't even test your redundancy, you have no redundancy. You literally just wasted all of that money. You wasted money, you wasted time. And yeah, just I don't know why it upsets me so much, but just the idea of doing all that work and then not checking that the work is even correct. So when you're doing commissioning, if you have any redundant networks, and it's even true with conventional substations, we use an older technology called RSTP, commonly where we have multiple paths through a network. That's the one that does have time for the network to reconverge. I would still even test my redundancy with that, where I would cause a network failure and then make sure my network comes back up and self heals. So that's a really big one that's very important to me. Another one is physical media connections. So you can think about it in terms of just normal copper as well, right? That like even on a car, that people's cars won't start and they bring it into the to the shop and the people will tell them, oh, it's just a loose connection on your battery. Similar things can happen with your communications where they like kind of work, but then like you turn on a big motor and it causes vibrations and all of a sudden you have like a network dropout. Those are all things we should be testing during commissioning. But again, we don't have the time or capability to test every single port for every single scenario. So usually we do the kind of physical media connection test at the same time we do our other tests. By basically, we do like a long-term signal verification. And if we ever lose a communications during that, we go and investigate that port, but we don't necessarily go through and check every single port's physical capabilities, like is it actually accepting cables properly. So in the sorry, is there a question?
Is the test done in substation control room?
The test would be, yeah, in the control house, normally in a substation, because that's where most of the networking equipment would be. It has to be protected from the environment. We generally don't put anything networking related outside in the yard. Like there would be a couple things, maybe like we need like obviously our GPS antenna would be out there, but that would come in on coax. So yeah, usually everything's going to be in your control house.
Yeah, thank you.
Yep. So part of the difficulty with this too is we don't necessarily have great tools to test this network functionality. We can test individual ports pretty well. It's hard to test on a wider scale. I don't know with the like aspects of AI that are coming and everything, maybe we'll have better options to test that like every possible scenario works on the switches. I'm not sure exactly where we're going there, but um, as of right now, we're kind of stuck in that kind of phase of like we test literally one thing at a time, and there's only so much we can test in a certain amount of time. So we leave a lot of potential for failure. So one other aspect too that has come up a lot recently and was never really a concern before this is doing like latency and bandwidth testing. So with a conventional substation, we needed like 1 millisecond of time synchronization accuracy for a sequence of events reporting. So that's a value we can test based on like, are we getting our actual time synchronization? But other than that, we weren't like really testing a lot of like the actual network aspects. And I guess even in that case, that's not really a network component. It is now with PTP. But with switches, we're sending a lot of traffic on this network, and it's something that I've noticed a lot recently, and it's kind of a gray area, so it's hard to test this properly. But I've been even suggesting now we should be doing more latency and bandwidth tests. And so what I mean by that is if we are dealing with a digital substation, right, we're sending protection signals on an Ethernet-based network. And so with that, we send goose messages to send a binary signal, so something that's just on or off, and we would use our sample value streams to send analog information, so like analog waveforms. With a goose message, there are actually these specifications that are set out for like how fast does, or yeah, like what is the maximum amount of time a goose message can take to get to from point A to point B for it to be protection grade. And the numbers are basically like 3 to 10 milliseconds, depending on which thing you're actually looking at. So my suggestion is actually now to start doing some latency testing to make sure that these are actually operating in the time scale that you're expecting. So with a latency test, if you're looking at a goose message on a digital substation network, you should be actually seeing the goose message transfer from like point A to point B in a few microseconds. So like somewhere from 10 to 100 microseconds, depending on how loaded down your network is. And then the rest of that 10 milliseconds I was talking about is actually processing delay on the sending and receiving IED. But the reason that I suggest to test this is kind of twofold, is A, it makes it so then if somebody asks you later, like they're saying like, hey, this goose message failed to operate like the device in the time that we are expecting, like this is your fault. If you can bring up that document to say, hey, when I commissioned this system, the latency showed that these goose messages were fine. But again, that's something you need to think about is we have a huge amount of network ports, right? We can't test the latency of every port to every other port, right? So I would theoretically draw a network diagram, or hopefully you already have a network diagram for the substation, and you pick the points where it would be the worst case scenario. Like what is the most amount of equipment this goose message could possibly go through? And I'm going to test from that point to this other point, and that should be my like worst case latency. So the reason I would want to do this is I can't give you an exact number. Like I can't say, oh, it should always be 10 microseconds, it should always be 50 microseconds. Basically, you want it under a few hundred microseconds, but also it kind of gives you something that it's like a starting point, like a baseline. So then you can like try different things on your network, like maybe load down the network with a huge amount of bandwidth and make sure that latency then doesn't go out of spec. Or cause a redundancy problem and make sure your latency is still fine during a redundancy failure. And so now that you have like a baseline latency, and during all of those other tests, you can make sure that your latency doesn't get like absolutely crazy. If it does, now you know, okay, we have some problem during these other weird scenarios. But then you only need to test like 1 point of latency. Like it'd be better if you could test more, but again, we don't have infinite time. And then along with that, bandwidth is another aspect that I think should be tested a lot more than it is, because the bandwidth should be able to tell you, does your network design match what you implemented? So we have generally a pretty good idea of what traffic should exist on a substation network. Like a bandwidth test, I think would be pretty useless on a IT-based network because you have all kinds of users all the time showing up, plugging in like their different laptops, their cell phone, their desktops, whatever, streaming Netflix, things like that. Those are things that are not happening on a substation network. Your substation network's traffic should be very, very consistent. And so I like to test bandwidth because then I can check it against what am I actually expecting to be there. So I've mentioned right now those two different protocols in 62850 for a digital substation, goose and sampled values. So a goose message is like a binary 1 or 0. There can be other stuff in there, but basically they're very, very small messages and they're not going to use a lot of bandwidth. A sample value stream, on the other hand, we're sending the representation of an analog waveform on the network that is a lot of bandwidth. And so we can actually calculate based on how many sample value streams we have, how much bandwidth we should be using. And so then you can do a bandwidth test at a few different points in your network, and you can see, does my bandwidth match my expectations? And that helps in both the positive and the negative case. So if you know that you have like 6 sample value streams and a sample value stream is around like 5 megabits per second, you should have about 30 megabits per second, plus a little bit for some goose messages and maybe some DMP3 or MMS, whatever. So you should be looking at somewhere a little over 30 megabits per second, so like 31, 32. So if you plug in a device that can take a look at bandwidth and you get 15 megabits per second, you should be thinking, oh, okay, something's going on here. I only have half the bandwidth I'm expecting, so I'm missing data. Or if you plug it in and you get 200 megabits, again, in the other direction now, you know there's something wrong. So it's a test that I kind of like just as a sanity check. But then the other aspect of that is you should be knowing your network well enough that you should know about where the bandwidth actually is. And so it can also kind of force people to actually go and look at the network diagrams and make sure they understand what they're even testing in the first place. And that's again where a lot of like field engineers make mistakes is they don't understand the network itself. So it's difficult for them to test the network properly because they don't know what is right and what is wrong, basically. So that's again a test that I've very, very rarely seen actually done, but I think it's valuable to just kind of also establish like a fingerprint. So then you know when that device, that network was commissioned, you had about 30 megabits on the network. So if somebody comes in 6 months later and they do a test and now the bandwidth is at 400 megabits, they can say, okay, something changed. And when it was commissioned and operating properly, we had this much bandwidth. Now we have all this used. Where's all that coming from? And they can take a look at it and find out that somebody changed some things without telling anybody, things like that. So these are all aspects of testing. I know that was a lot of information that that I would kind of like to see done better. I'm not saying we do a bad job right now. It's just something that I don't think has been the focus historically, where we have done a really strong focus on protection testing. That's done very well. We have a lot of room for improvement in the network testing in general. And with digital substations coming, that's a very, very important aspect we need to figure out. So in terms of the IEDs themselves, we also need to commission stuff. So what I was just talking about there was the network itself. So we have like an Ethernet-based network with all these switches, but it's really only going to pass the data that we give it. And so then on the other side, we also need to commission all the IEDs themselves. So for example, a network switch, if a goose message arrives at it or an MMS message, it's just going to send it to wherever it needs to go, but that doesn't mean the right device was plugged into the right port, basically, or that it had the right things configured. So we also need to take a look at the IEDs themselves. This can be a little bit more difficult. A lot of the times how they actually commission these things is they just plug them into the network, all the devices, and they make sure that they can communicate properly. As long as they can, they walk away. They don't actually double check a lot of these things. And that is actually, again, where I've seen some failures is, for example, I've seen it before where there were duplicate MAC addresses on the network. So devices were basically by accident pretending to be other devices. And because of that, there were some failures. But during the commissioning phase, it actually looked like it was correct, just because they would update something and the other device would update. What they didn't realize is that if they updated this other completely random device, it would also cause something to change on this IED, which was completely unexpected. That was a negative test case that they never could test for. So the way we actually test these communication parameters generally is we'll take a look at the configuration files themselves. So for an IED, like a SCL relay, we would use Quickset and we would go through and we'd make sure all the files match our expectations. But then theoretically, they would also check that against what exists in the relay using the front panel. And I think that is generally a pretty good procedure because then you can verify not only that the files are correct, but then also are those the files that are in the relay itself. So if you go in through the front panel, you can say like, okay, what is this device's IP address? And it will show you it's like 192.168.50. Whatever. And then you look at the actual documentation and make sure that that matches and you go through line by line. The only really big problem there is it's time consuming. And then it's a human doing it and humans are very prone to errors. Another big one here, I guess, would be TCP UDP ports, but this one at least, generally, if those are wrong, devices won't communicate to each other. So that's kind of actually a self-testing functionality there that it would have to be misconfigured in the same way. So it would have to be wrong in both different devices in the same way for them to be able to communicate properly. So basically, if somebody messes up a TCP UDP port, in terms of communication parameters, then it will just not work, and they would catch that during commissioning. So there's a lot of different things to verify for all of these different devices, and that is generally how we actually do verify our communication parameters, is we just make sure it can talk to the other device. I think there is some room for improvement again there because of, like I said before, about the theoretical duplicate MAC addresses or IP addresses on the network. Um, but those are somewhat rare problems. Another thing that we'll generally test is our signal mapping. And I kind of already mentioned that in terms of the gateway, but we also do that with all of the individual devices. So with multiple IEDs, we not only make sure that they can talk to each other, but that when a device is sending a certain status, a certain signal, then it's interpreted correctly by the other device. And so one of the reasons that's really, really important is because we have these different types of addressing systems for protocols. So we use Modbus, DNP3, and 62850 very commonly. And essentially, how these work is that you have a certain piece of information in a certain memory location on one device, and then it will send it over the network to the other device. And you have to configure that relay properly, or IED properly, to take in that information and put it somewhere in itself. If you misconfigure where that data should go, it's going to affect something different than expected in the IED. It's still going to accept the information, it just will affect something else. So like you could send a signal that's meant to like open a breaker, but instead it turns on an LED or something like that if somebody misaligns something in the data maps. So generally, again, we'll go through the IED and make sure that when we trigger anything on the other IED, that we like have a checklist and we make sure these things happen properly. Again, it's very time consuming and we have humans involved and humans make a lot of mistakes. So this is something I've seen quite a few problems from, is that people will miss where things are misaligned, and then it won't be found out until like 6 months, a year later, when somebody's looking at some data and saying like, hey, the breaker says it's open right now, but I can absolutely see that the breaker is closed out in the yard. And then basically they find out like, oh, okay, this was never commissioned properly, and then some angry emails get sent out and somebody has to actually go out and fix it. So basically that's kind of the overall idea of commissioning. And so where I wanted to end it today, actually, we're going to get done a little bit early, is on this diagram that I introduced actually in the first class. And now hopefully it'll make a little bit more sense to you as well. So I kind of wanted to reiterate a little bit of what we talked about over the last 3 days of lectures. So this would be a diagram representing the communication infrastructure of a digital substation. So the reason this would be a digital substation is what we see down here, where we have these different like current transformers and voltage transformers tied into these devices that then send the information on an Ethernet-based network. So the difference between a conventional substation or a hybrid substation, some people might also call it, versus a digital substation is, if this was conventional, then these signals here, like the switchgear, the CTs, the VTs, they would, instead of going into a merging unit, they would go directly up to these relays, and these switches, this Ethernet network down here, would not exist. So this is called the process level. And so the process level in a digital substation is Ethernet based, and in a conventional substation, it's copper hardwired based. Then everything from here up, though, would be basically the same in a conventional or a digital substation. So we have these different relays that are actually performing our protection functions. So they're doing things like looking at the current and voltage to make sure if you have an overvoltage, overcurrent, that they're going to send out a signal to then actually operate switchgear based on it. And then even in a conventional substation, we have this network up at the top that is going to be Ethernet based. And so you can see like a network switch there. And then we have the different stuff that would be connected into it, such as an RTU up here acting as a gateway. That's where our signals would be sent out over a wide area network out to the control center. So this is the historical SCADA system that we've had, everything that's up here. People are pretty familiar with that. That's been very well designed. The process level stuff down here, that's where it's very new, and like the digital substation stuff is actually coming out. So we have kind of those, we're trying to apply some of the ideas from the SCADA network up here, but we're finding out that we do need new technology and new ideas for this process level. So, I mean, that is basically all of the content I had. Do I have any questions over anything we've covered in general or anything that's on this diagram here? So you're all SCADA experts now, ready to go out into the world?
I guess no, but I did have a question. At what
Yep.
layer are you mostly worried about cybersecurity influences? Or
So, okay, I really like that question actually, and this is a good diagram to illustrate that. That we worry about attack vectors in terms of like how can somebody actually access this stuff. So the process level stuff down here would be in a digital substation is absolutely like that's where attackers want to get because if they could get down here, they can mess with the actual switchgear and then cause the most disruption. But that's also the hardest place for them to get. So that's actually why we have so little cybersecurity on the process level, because this isn't connected to the outside world in any way. You would have to attack one of these relays first from the SCADA level network to then get information down onto this process level. Because we don't allow people to just like walk in and plug anything into our process level network. So in terms of cybersecurity, where we're really worried about things is like it's not as big of an issue if it does happen, but it's the more likely scenario is this substation level network being attacked, and that's generally from any remote access points. And then also from these engineering workstations. So, for example, during the Ukrainian cyber attack, there were a couple different ones. So, like one was somebody like dropped USB drives in the parking lot, and so people plug them into like engineering workstations, and then that would spread a virus on the SCADA network. Another one is that somebody was looking at emails on one of the workstations on the SCADA network, and there was one that was supposed to be about like company bonuses, and somebody opened an email that had a virus basically, and it attacked the substation level from that. And then the other aspect there is that sometimes the SCADA level is actually connected out to a wider area network. The remote access is the most likely place for a substation to be attacked. It's not like we attach these directly to the internet. It's more just like it's a connection to the outside world in some fashion, and it's a lot harder for us to control anything coming in from the outside world. And so that's kind of our worst case. Like that's where the most attacks are going to come from, and that's what we lock down the most is like with firewalls and everything up here. Does that answer your question?
yes, thank
How
you.
it is done on, uh, the cycle time of the test on substation?
Sorry, what was that?
The cycle time of the test on substation, how far supposed to be?
How fast should the cycle time be?
Yeah, the test to be done by minutes, by hours, by day.
Oh, how long does
Yeah,
commissioning take basically?
yeah,
Yeah, I mean that is hard to actually identify. And it depends on the quality of the field engineers, how good the design actually was in the first place, how good the prints are actually given to the field engineers. Like they can only operate off the data they're given. And then it's a question of is it a greenfield where they're doing literally commissioning on something that's brand new, never been there, or is it a brownfield with very slight modifications? So it's hard to give you a good answer, but um, I would probably say generally in the couple of weeks to 6 months for commissioning. But again, that's a really hard question to answer. And again, it also depends on the size of the substation. A little local distribution substation is going to be very different than a transmission level substation.
yeah, thank you.
Mhm. Anything else?
Does the test end up to the overhaul or maintenance of substation?
So we do, in terms of protection testing, we do actually do a maintenance schedule where we do retest protection IEDs every 5 years, and that's actually government mandated. Currently, there aren't government mandates on recommissioning or retesting the network. I do think that that's coming at some point in the future, but I think more what they're waiting for regulations is like we don't actually know what fails. We don't have enough data from in place digital substations to necessarily say like like we need 10 years of data to know what actually fails, so then we know what we need to test. It's kind of chicken and egg scenario going on there. So with protection, we have a very solidified protection, like a testing schedule. Generally with the network, it's only really done during the commissioning phase.
Yeah, thank you.
Anything else? All right, well, it's been fun. Um, hopefully, hopefully the content was in your wheelhouse. I know a lot of it was pretty advanced in terms of communications, but with only a few hours, that's basically SCADA in a nutshell. I gave you some of the historical, like what it is, and then what the future is coming. But obviously, it's a very large topic that there's a lot more to. If this stuff interests you, I do teach a class in the fall. That's based around communications. We go into everything I talked about in more depth. But the other aspect would just be learning network communications in general. The ideas of Ethernet are very applicable from IT into this world. So really any IT based things that do focus on like the network level are valuable for you in this space. But we do have some things that are pretty specific. I mean, for example, PTP is actually not, it's something we use for time synchronization on Ethernet networks in utilities, but it's actually widely adopted. It was originally used for the telecom industry, actually, to time synchronize cell phone towers. And Facebook uses it in their data centers. So a lot of the stuff, you can learn it in other fields and then apply it to the utility world. But really anything Ethernet-based communications would definitely help you with the topics we've covered.
Do you have any homework for your three session instruction?
Yes, and I did send that to Paul, so you can ask him when he would be posting it.
Oh yeah, okay.
All right, anything else? All right, well, hopefully that was. Oh, Rob, were you?
Oh, I was just going to say thank you.
Yeah, no problem. It's a good time.
Thank
So
you.
Yes.
hopefully I'll see you all around.
See you
Awesome.
all. Thank you.
See ya.
Thanks.
Thank you.
Yeah,
Thanks, Pascal. Have a good one.
bye.